Okay. So as the title talks, it is going to be networks and cybersecurity components. And the agenda or the objective of this presentation is to give you a bird's eye view of how you have to look at when you are into a consulting role, be it as a QoS security consultants, or you are going to be a Purple Synapse trainee or a researcher. And also it is contextually relevant for all the sales and pre-sales team people. Maybe they will not be doing the entire role, but this is at least expected from all of you. Just give me a minute. Yeah. So this particular session, we are going to discover the insights that we are going to apply based on the roles which we are going to do or are already doing it in our current job functions. And it will be taking care of three different parts in the through the presentation. First, we will focus on the networking components because they serve as the building blocks of what we do and why we do what we do. Secondly, we'll be talking about how the packet moves on the wire, because if we understand that, putting a cybersecurity for that becomes quite interesting and easy for us. In the second part, we are going to talk about the servers and the applications, because once the building blocks of the networks are done, then we perhaps need the application and servers to be hosted on the top of it. I still am hearing some noises. Would you please mind putting all of you on the mute? Thank you very much. Servers and applications, because they also become the second tier of the building blocks once the network components are set in place. And also in this session, we are going to discuss about the evolving computing assets, because the entire security strategy in the current times expects to work or deliver the desired objectives for the existing way of doing server and applications business, and also the way they are evolving by the very existence of the cloud, mobility, and various other abstractions that exist by the combination of cloud and mobility. So this is the second part, where we are going to then subsequently have a 30 minutes break, and then we'll do a long session of part 3, which is basically understanding the cybersecurity controls. And I will actually, based on my experience of having worked with large banks, both in the Indian subcontinent and outside in the global context of Western world, I will just be talking about a very, very basic architecture, how at a high level it looks like, and how whatever we're going to learn in the network and the application security stack in the current evolving times, how to learn the basics or cybersecurity controls or the contours that are going to fix the cybersecurity objectives. Now, to start with the first part of the presentation, that is the networking components. The most, again, I request everybody to please put it on the mute. I'm not sure why this is not being understood. Okay, so the most fundamental thing which each one of us, maybe whether in a sales, pre-sales, consulting, or a delivery PS role, we need to understand two aspects of a network identity. One, which is a physical address, how an entity is going to be recognized on the wire or on the network. And in this, we typically in a very standard format call it as a MAC address. MAC address is unique 48 bits binary number represented in a hexadecimal code. So we all know that each hexadecimal number can be represented by 4 binary bits. So if I divide 48 by 4, we get 12 hexadecimal digits. And each of those hexadecimal digits are combined in 2 digits separated by a colon or a dot is a very standard generic representation of a MAC address. No matter you are a LAN device or a Wi-Fi device or a Bluetooth device, when any device that publishes itself on the wire or on the wireless infrastructure, it gets recognized by this unique ID. And the first side of, or the left side when you are looking towards the screen, which is, for example, in this case is 000A95, something like that, defines the vendor IDs. So we know that there are many vendors who give the network interface cards or the Bluetooth, like we have Broadcom, we have Surecom, we have various other different network interface device vendors. So they get those respective unique codes. And then the subsequent digits are basically recognizing each of their hardware that they are supplying to the industry. Now, in a physical world, this is analogous to my city having these names like what we see in Bangalore, New York, or anywhere part of the world. So for example, if I am in Bangalore, we get to hear Commercial Street, Brigade Road, Ashoka Pillar, and so on and so forth. When we are in Delhi, we get to hear these names like Lajpat Nagar, like Krishna Market, so on and so forth. But if we sit at a network level where all these cities connect together to make one country, it is very difficult to recognize these identifiable numbers, these names, which is basically by their name, you cannot understand which part of the world or the country or the state or the city this is going to belong to. Please mute yourself. I am requesting. So this basically is a hardware address which makes the machine recognize. So now to this, if one has to make this device as a part of a larger network called country or a larger infrastructure called continent or a globe and has to still get recognized, then we need to use some logical scheme of things which people can memorize, visualize fast, and also we can provide some mathematical computations to process the paths. This means that source to destination paths can be orchestrated as and when required. So we know that in the similar analogous space of the addressing recognition, we have something called as the PIN numbers or the zip codes, which the global identification schema allows us to basically route any packet or envelope from anywhere to anywhere. So this similar way, the larger space has been recognized by virtue of an IP address. A typical version 4 IP address, we most of the time see it on our laptops, our machines, etc., is a 32-bit code. Also, we are living in the era of a version 6 for almost a decade now, and this is a 128-bit address. Basically, whether it is a 128-bit version 6 address or a 32 bits version 4 address, it is having always two parts. The first, which is seen on the left side, is a network ID, and then within the network ID, the remaining part on the right side of the addressing space is the host ID. So these are few things which we need to understand when we start to get into the basics of networking. And to visualize this in a postal system, we have already given you an example that pin numbers or zip codes, they make the logical understanding of which place a packet has to be delivered gets very easy. Similarly, the pin numbers in itself are not once the packet reaches in a local network very easily get addressed to. So for example, if I am sitting in Mumbai and I tell somebody that okay, go to 400050, nobody will understand that it is Bandra West. Nobody will understand if I will tell that okay, go to 110019 in Delhi. So nobody sitting in Delhi will so easily understand that I have to go to Nehru Place. So they will need a translator in the form of a table which will translate that zip code or a pin code into a equal physical address. Similarly, in the networking world, a packet cannot reach to an IP address of its own. It needs a translation to a MAC address for a packet to get eventually delivered to the final destination, because the final address is a physical address. That's how the networking works. And moving from here, I know most of you must have already been aware about this. We are going to delve into the devices that are helping us move these packets, because until and unless the data packets will move from a client to a server and a server to a client in the both directions, our end objective of applications that we use today will not be achieved. We sit in our house and are able to do this Zoom call is by the function of some machines coming in between to make this voice reach from the place where I am sitting to the place where you all are individually sitting. So for this to happen, the first building block is a networking fundamental components. And for that, the first level device which starts doing or routing or moving the packet from one place to the other is called as a switch. Can you mute, please? And it won't be good. Okay. So coming back to the first part, which is the switching. A switching happens in the very localized network, where we move the packets or we forward those packets as frames from one physical port to the other physical port. You can very easily see that this picture has been copied and has been designed by a company called Vexels. So the attribution is there below that, which is showing you the multiple physical ports switch. So it's a rack mountable hardware device which has multiple switching ports, and the packet or a frame of data can move from one port to other port by the virtue of a very specialized hardware chip. And this specialized hardware chip is sometimes is also called as a application specific integrated circuit, ASIC. So the whole purpose of this ASIC is because it basically delivers a very high speed forwarding or switching of the data frame or a packet from one port to the other port. So that's the first part which each one of these ports will do. So if you can count, you looking at this particular front panel of the switch, there are similar looking ports. If you start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 into 2. So there are 40 ports which are on one side of the jacket on the front panel. And then I can see another different type of 4 ports on the other side of the jacket. So this makes this total as a 44 port. And then on the extreme left, what you see vertically placed, those green lights, those are basically the indicators of the switch functioning, called as LEDs, which captures its functionality. And I'm sorry, some pet behind my other house is doing this continuous disturbance. Okay. Then if you look at these two kinds of different ports, which is 40 ports, these ports are called as the downstream ports. On the downstream ports in the network, generally you will connect a desktop or a laptop or a server on the downstream side, which in the most typical current scenarios is either a 1 gigabit Ethernet port or a 10 gigabit Ethernet port. So all those 40 ports which you are seeing are either of these two kind of ports, typically in the current generation of switches. And then on the right side, which you are seeing 4 different types of ports, they are typically used for upstream function, which means this switch in itself is going to enable these 40 machines which are localized in one single building or a single campus or a single floor to talk to each other or get connected to each other. But if they want to be connected to a larger part in the internet network, then obviously this entire switch needs to be uplinked further to the next set of devices. Hence, this uplink is typically in the current scenarios a 10 gigabit Ethernet or a 40 gigabit Ethernet or a 100 gigabit Ethernet single interface ports. Is anybody having a question here? Are you guys?
Hello?
Padma, only you can answer, or anybody, one Vishnu. Are you hearing it well?
Yes, sir. Yes, sir.
Hello?
Thank you. Thank you. Thank you very much.
Hi, sir. This is,
Yeah, everybody can mute. Thank you. Thank you. Now these switches are either a layer 2 or a layer 3 switch. Now this is very important for us to understand and recognize that this definition of layer 2 and layer 3 comes from OSI internetworking, wherein the layer 2 is a data link layer and a layer 3 is a network/IP layer. Now, all of those who are not aware about the OSI stack may Google this after this session and understand what exactly is a layer 2 or a layer 3 is. But for the sake of connecting it to the previous slide, the MAC address which we saw, the address where the physical definition of a host or a machine is defined, that is happening at the layer 2. So it's a layer 2 address. MAC address is called as a layer 2 address because it connects and understands at a physical layer level. The IP address, whether a version 4 or a version 6, this basically is a function of routing the packet in the internetworks space. When they are all connected, multiple networks are interconnected. So then we will need a layer 3 routing or layer 3 switching. While when we are inside one single segment, like I have told you, in this switch, you can connect 40 devices to talk to each other. When all these 40 devices will talk to each other within single campus or a localized space, then they will only need probably the MAC addresses for each other to communicate with. But when this switch will start getting hierarchically connected to a next switch and a next switch and a next switch, and this becomes a very complex infrastructure called internet or internet work, then obviously these MAC address will no more be sufficient, or the switching between these 40 ports will not be sufficient, that this switch needs to keep on moving the packet to the next hop level. And for that functionality of moving the packet to the next hop or to the next switching device is generally the layer 3 switching. So layer 3 switching will only be possible when we are using layer 3 addressing schema, and layer 3 addressing schema is the IP addressing schema. Now let's look at coming back to a layer 2 switch. So imagine what you are seeing physically like this device in this slide, when it goes and gets connected and start connecting local infrastructure in my company or in my office or in my building or in my campus or on my shop floor area, it connects these devices together. So we are seeing in this diagram, some warehouse server. So this is an example of warehouse automation. So we have some warehouse servers. There is some workstation of a warehouse guy. Then you can see some label printer is there, which is going to do a printing of labels. And then there is a Wi-Fi access point, which will allow us to connect some point of sale devices, which are shown like mobile wireless terminals or some other stationary terminals, which are being shown as kiosks on the floor of warehouse. So these Wi-Fi devices are connecting to a access point, and then this access point goes directly to a switch, which is seen and represented as a switch. And then also the warehouse server and the workstations are connecting over the wired connectivity to these switches. So this is like a layer 2 switch, which has allowed the connection between multiple devices to work together. And for this, it only needs a MAC table. So what a MAC table is, the MAC table is basically helping the machines understand that which all MAC addresses are directly connected on that physical port. So if we look at this picture again, let's say all these ports which I am showing you through the mouse, I'm not sure if you are able to see my mouse, this is the mouse here. All these ports here are, one minute. So these ports are the ones which are represented as, let's say, gigabit, GIG, one slash one, which means this port is one, this is two, so this will become then gigabit two, and then this is three, so on and so forth. So this way, this is the representation on this switch, and this basically is, let's say, a gigabit Ethernet 40 or a higher level port. So this may be like this, GE 2/1. So you can see the difference here. It is first is two and here it is one. So this basically helps us understand that whether it's a downlink, uplink, or it's a downlink stream 1, stream 2, and so on and so forth, depending upon that nomenclature of the ports, you can figure it out. So now if we look in this scenario and try to go with this table, it shows that okay, so there is some mistake I have recognized here. Sorry about that. It should have been G 1/1, 1/2, and 1/3. So please read it that way. It's sorry about that. I somehow written this wrongly. So it should have been gigabit Ethernet 1/1, gigabit Ethernet 1/2, 1/3, 1/4, 1/5, 1/6, so on and so forth. So let's say on that gigabit port number 1, physically only one machine, one desktop, one laptop, or a warehouse server is connected. And that server, the moment that server or a machine will switch on, it will register its MAC address on that port, which is then written in the switch MAC table, because now the switch is aware that on my port number 1, this particular MAC address is sitting. Similarly, when on the port number 2, let's say a different device register itself, it says that, yeah, on me, I can see 00.0a/95 and so on and so forth. That kind of a MAC address, which means it's a different machine on this particular physical port. Something interesting, which you will see on gigabit Ethernet port number 3. Now, this 3 number port is the one which is connected to, for example, the access point. Now, the access point is further having some Wi-Fi devices which are connected to that. So, on that port, it means access point is seeing 3 different MAC addresses because 3 machines have switched on themselves. So, the same access point will tell that all the 3 MAC addresses are sitting on my Wi-Fi infrastructure. So, the switch MAC table, which is further connected to a access point, will now say that all 3 MAC addresses are sitting on this one single physical port only. So that's how a MAC table starts getting to built. And once the MAC table is built inside the switch, which is by virtue of now assuming that machines have switched on themselves, then the machine starts talking or communicating to each other. And when that will happen, what a switch will do is, the moment a workstation wants to go to a warehouse server, the MAC address of the server will be called for, and in the data frame of the workstation, which the workstation is trying to send the packet towards the warehouse server, is it will show that the destination MAC address is that of the port number of the warehouse server that is registered on port number 2. So this way, the translation table for moving the packets from one port to another is delivered by virtue of the MAC switch table inside the switching. So therefore, all communication that happens at the layer 2 level will be accomplished by virtue of switch that is doing only a layer 2 function. And in that, it only needs a destination MAC address in the data frame to switch or forward the packet to the respective physical port where the end machine or the end compute device is connected. This way, we understand how the layer 2 switching is being done. But then, when we move to the applications which want to talk to each other, let's say they want to now not only restrict themselves to be communicating within the warehouse, but this warehouse workstation wants to connect some website because it also wants to check whether my bank is supporting this particular bill, or is it going to accept this particular e-check. So then the bank has to be communicated through internet access. So here we are taking an example that a user wants to go to abcbank.com, and the same user is also doing some course with Purple Synapse. So they may want to come to Purple Synapse or to QS Technology website parallelly. So this all names which we every day put it on our browsers to access those respective application servers, these names are called as the fully qualified domain names, also in a short acronym represented as FQDN. Now, I either by virtue of my browser or by any other interface like iOS or an Android app, whenever I am trying to go towards an application server on the other side, we need the first thing to resolve that fully qualified domain name to an equivalent IP address. Now, when an equivalent IP address is desired, we all need to go to a global system which is recording each and every fully qualified domain name on the internet and translating it to an equivalent IP address. So that system is called as a domain name system. So if we go back to this again function and come back and say that, okay, this workstation wants to go to his bank abcbank.com, the first thing which he will require that will happen on his machine without his knowledge is the domain name system resolution or a DNS resolution, where this abcbank.com will get recognized and resolved into a equivalent corresponding IP address. Once this, his browser in the back end, without the knowledge of this user, has already resolved this domain name to an IP address, the next thing which has to happen is that this browser has to start pushing the first packet for a HTTP GET request, so that the HTTP goes out of this machine to go up to the bank and get me back the website of the bank. This packet will not start moving of its own on this wire. The wire is here physically connecting this workstation to a physical switch. And we all know that for that to happen, the workstation needs the MAC address. MAC address of what? MAC address of abcbank.com. But how will I get to know the MAC address of the abcbank.com? Because abcbank.com is not sitting on this local switch. So therefore, abcbank.com will never have a MAC address of its MAC address registered on this switch. So there is no MAC table that can take this packet to the next level. So how this layer 2 switch is going to work? That's where we understand the limitation of a layer 2 switch, that it cannot carry the packet to the next level. So what it needs is, it needs a layer 3 switch now cascaded in the next level or in an upstream. That layer 3 device will take this packet towards the internetwork. And now this particular workstation should be able to push this packet to the next hop, which is his router or his layer 3 switch. Therefore, instead of doing a ARP resolution for a IP address to a MAC address for abcbank.com, it will do a ARP resolution for the router or the layer 3 switch connected in my LAN network or in my segment network to take me out of this segment and move it next towards the internet. So ARP resolution still will be required, but this kind of a ARP resolution, where instead of abcbank.com MAC address, I look for my router or my layer 3 switching device address, so that I can move the packet from my workstation towards that device, and then that device job is to forward it subsequently on the logic which has been written into that device, is the ARP resolution for a router. Such ARP resolution is called as a remote ARP resolution. While in the previous case, when a MAC address to MAC, even if this workstation was connecting to a server using the IP address, this also was requiring a MAC address to be resolved for the server. And that resolution I have already explained you, that where the local IP address gets resolved to a local MAC address, that's called as a local ARP. And when we are going outside my network segment, instead of getting a MAC address for that internet device or a outside networks device, I get responded with my local layer 3 routing device MAC address. That ARP resolution is called as a remote ARP resolution. Okay. Any questions here?
No, sir.
Okay, good. Thank you very much. So then from here, we start to see how a layer 3 switch works. So on the right side, you are just seeing a very, very well connected some switch, and we will believe that it has a layer 3 capability. So please always understand that whenever I will say it's a layer 3 switch, it will always do the job of a layer 2 plus layer 3, which means it is capable of switching the packet within the segment and also routing the packet towards the internet or to the other connected networks. So it's a layer 3 switch which is used for connecting a segment and also towards the external world. If I go 20 years back, when I started my career, the layer 3 switches were not there. It was only a layer 2 switch, and then the layer 3 functionality was being done by the router alone. Now, what was the difference between that 20 years old device called router and a layer 3 switch? In the current time, when we are in the year 2020, where we have seen that the routers have actually or gradually evolved to something called as a layer 3 switching. Fundamentally, these two devices, a router or a layer 3 switch, are fundamentally one and the same thing in the current when we are talking in 2020. So don't get confused. Even if you see me speaking the word router or you get to hear the word routing somewhere, it is anything which when we say a routing, it is nothing but a layer 3 switching in the current times. Now, why we used to call routers and why we are calling this today's scenario as layer 3 switch, I will distinguish this in the next couple of slides. So till that time, park them. Till that time, believe that yes, it's one and the same thing. So a routing part of a layer 3 switch basically needs the remote ARP management, while the switching part of the layer 2 functionality within that layer 3 switch only needs a MAC table, the MAC table to switch between the ports. So switching between the two ports on the switch will always happen through a switch table that I've shown you in the beginning, that is called as a MAC address table. But the routing will need either a remote ARP or it will need some more smart advanced functions that we are going to talk in the subsequent slides. So for that reason, just for a simplicity's sake, take this table from the way it looks like as a logical table, that on one column we have put in all the IP addresses. Typically looking at this, whichever address looks to me as a local, the local MAC address is registered. Here the port numbering is quite correct. Sorry about the first slide, but here the port numbering is correct. So here you look like gigabit Ethernet 1/10, 1/12, 1/17, 1/14. All these are the ones which are having local devices connected with the similar looking IP address, correct? All three things in the first part of the address are looking similar, 192.168.10, which means they are part of a similar local segment. But then you start to look at the ones which are shown with the bold color, gigabit Ethernet 1/1, 1/1, 1/1, and 1/1. In this table is coming at 4 different places. One, it is coming for 192.168.10.1, which means it's my local router, or a local. When I say local router, means it is my layer 3 function within this physical switch. And anything which requires me to go outside the outside world, outside my network, whether it is a IP address 203.54.15.1 or 97.53.157.209 or 111.10.202.15. So looking at these numbers, we all know that they are appearing to be outside my purview or my local network. And in such scenarios, I will always need to go through the layer 3 function only. And that is physically registered on port number gigabit Ethernet 1/1 and given an IP address 192.168.10.1. So this is how you will see the packet when it starts from a local LAN, be it 192.168.10.2 or 10.76. Whenever it wants to go outside, it will use this particular physical interface 1/1 to go out of this particular boundary of the network. Then the come very interesting line, which is the last line. The last line is a gigabit Ethernet 1/24. And this also is appearing to be a remote ARP written here. While if I look at the desired IP address, this is 192.168.11.19. Now 192.168.11 is different from 192.168.10. So that basically means that it is outside my one local domain or my boundary. But because it is .11, most likely it is appearing to be one more office within my own building, one more campus or one more building within my own campus. And the connectivity to that is not local, but through a layer 3 functionality. So when we say local, it means only MAC address local level 2, layer 2 level switching resolution is good enough. But whenever we are not in the local ARP domain, which means we are outside that domain. But because physically that particular machine 11.19 is connected directly on this switch, so this switch can seize its own MAC address in its MAC table as well. So this is how the layer 3 switches are these days. They will be having a combined table which will be combining these MAC addresses which they can physically see and which they can not see. But when you see a address 203.54.15.1 or 111.10.202.15, this particular switch cannot see them. So there is no direct MAC address of them, but my own route, my own physical device, which will take me towards them. So if you see that the 4 rows shown here, which have gigabit Ethernet 1/1 in the right lastmost column, you will see in between the MAC address written is common. All 4 entries have one common MAC address. Why? Because those 3 IP addresses does not belong to any device which this particular physically shown switch can actually see itself. Therefore, there is no MAC address in that table. But the MAC address of a next device or a next router or a next internet broadband device that is going to take this packet out of my switch, that MAC address might be the one which is registered on this particular port. I hope this is clear. Though this appears to be a little complicated, but I'm sure that all of you guys, even if you are in sales, need to know at least this much. Because if you know this much, you will be able to have a very good conversations beyond just that a global, what we call it as a glorified sales folks. Now let's look at what I have explained you with 4 different examples, and that will complete our networking fundamental scope. I'm sure each one of you can see this hand-drawn diagram. It has host A, B, and then there is a LAN printer. All these hosts have different IP addresses which are appearing to be in a local domain 192.168.10.2, 192.168.10.76, 192.168.10.193. And then there is one surveillance camera which is 192.168.10.107. All are connected to this different ports of layer 2/3 switch. So whenever I say layer 2/3, this is basically to actually explain you that this is physically a layer 3 switch, but it will also do the layer 2 connectivity. So whenever a traffic will flow in this example from one machine called client A machine towards the printer, let us understand how a traffic will flow. A client A has a print spooler on the local machine, which has to fire a printing request towards the network printer. Now the IP address of the printer is 192.168.10.193. the local machine which is having 192.168.10.2 will understand that this happens to be on my local network. Now, something which I have deliberately kept out of the scope of this discussion is subnet mask or a subnetwork address, because that is not very contextually relevant to all of us to understand. But I am sure that each one of you, even if you are from the sales or a non-technical domain on this session, you would have seen that whenever you define your IP address or whenever you look at your own machine's IP address, you always see beyond an IP address, there is one more written thing called as, which starts with something like 255.255 or something similar. That whatever you see, at least in the first octet written as 255, that is what is a subnet mask. So by virtue of subnet mask defined beyond an IP address on a machine, the machine decides, looking at it, that whether the packet which is required to be sent out of this machine's network card, whether that packet has to be sent locally or has to be sent to outside this network. So that subnet mask helps the machine to build a sense of its own local network or a local segment, that what is my boundary. The boundary is fixed by that 255.255 kind of looking component called as subnet mask. So subnet mask is nothing but a boundary between the network A, network 1, network 2, network 3, and so on and so forth. So in this case, just for a very simplicity basis, I am just telling you 192.168.10 is a defined boundary. So anything which will not resemble these first three numbers means it's outside my network. So coming back to this subject again at the same part. So now when we move to the step number 3 here, hence the client A will now initiate a ARP request, that is an address resolution, a protocol request. Why it needs to do that? Because the printing packet will not be able to move towards the printer on an IP address, because I have told you that the actual data frame or a packet will move on the wire when it knows that what is my next MAC address. Because on the wire, zeros and ones will only move when they know what is the next MAC address. Period. There is no other mechanism with which they will move. So in the wired or a wireless network, when in the local network segment, I understand that it is my local LAN machine itself, then we start a ARP protocol process. Our protocol process itself is a little complicated process. It starts with broadcast and so on and so forth. So I am not discussing that. Anybody who is interested and is looking at this for the first time can do a Google search to find it out. The most interesting part is that the ARP in this local domain will help me finding out the MAC address of the printer by a dynamic process. And once I know that MAC address of the where I want to go, I will start the printing packet from my machine client A towards the switch. And when that packet will reach the switch will look into its MAC table. Oh, this MAC is sitting on my port number 1/14. Immediately, it will start forwarding these packets towards packet coming from port number 1/10 will start automatically moving towards port number 1/14. This is what is a layer 2 switch function. This is so fast that these days, it's called as express forwarding. So the first packet only because printing, you will know that, if it's a 100-page document, there's so much of data which needs to continuously move. Only the first packet will go and find out which port of the MAC I have to move on, or which port of the switch I have to move this packet on. And then once the first packet is pushed towards this, then the forwarding or the express forwarding will start shunting all the subsequent data packets for printing between the port number 10/14 till the time this session is not over. So this is how this particular example shows how a traffic moves within the local network. You will get to see all these components. So this diagram will continue to survive for next 4 or 5 slides. So don't worry too much about looking on the other components. I will be explaining you this with the other examples the moment we reach there. So now comes the example number 2. In the example number 2, let's look firstly on what's written in the text. Client A browser requests for www.abcbank.com. So that's the request for browsing or for web I would want. Now, if that has to happen, as I've told you in the beginning of the session, that the first step will be a DNS resolution. Once the DNS resolution starts, what I will get at the end of the resolution, I will get a equivalent IP address. But now I know that the DNS server itself is sitting outside my network, correct? Now look into the again, come back to the diagram. You see on the internet, the machine which is shown above that cloud, DNS server, its IP address is 203.54.15.1. Now this DNS server is a Tata Communications DNS server, for example, or a VSNL DNS server, which is defined in my browser configuration or my machine configuration, not exactly browser, but my network credentials, which my browser is going to look at. So it will know that, yes, my DNS server is 203.54.15.1. So at the first level, the packet itself has to go to DNS for the resolution to start. So that's why in the example 1, in this slide, we are only going to see how to get to a DNS server to get a web address. So then what will happen now? Hence the client A will now initiate a ARP process to identify the MAC address of the next hop, because my machine knows that it is not in my own local network. It is 203. Forget about 192. So first octet itself doesn't match, which means it's absolutely out of my network. If it's absolutely out of my network, doing a ARP request for that machine will not solve my problem. So I need to do a ARP request for my router. My next hop, which is shown in the bottom of the diagram, with an address 192.168.10.1. So I am using the similar addressing schema which we have been seeing in the past, so that we all can build that understanding. So this router is the device now which is going to take me out of this network towards the internet. That's also in the technical definitions of network called as next hop. So next hop means the one which will take me out of my local boundary. So I will do a ARP resolution for this next hop. Once I get the ARP entry or a MAC address of this device, the device MAC address now on my machine will help me sending a DNS packet or a DNS query out. So now machine A is sending a DNS query out because now it knows the MAC address where this next query will be taken. So then a switch will work in a layer 2 role. It will look into its MAC table. It will know that the router, which is 192.168.10.1, is sitting on my port number 1/1. So I will push the packet to 1/1. Now the packet will come to the router and the journey will be started from a router towards the internet, which we are leaving from here on this slide. So which means my DNS query is out of my machine and I'm very happy because my DNS will respond back with an IP address of a web server called abcbank.com. Now that's what I was wanting, period. So my DNS server will respond my DNS query by giving me back an IP address of the DNS record that I wanted for www.abcbank.com. And this completes a DNS resolution. Now my machine, which is a client A, already knows that I have to go to a IP address 111.10.202.15, which happens to be a bank server, shown right in the bottom towards below the internet cloud, extreme right if you're looking towards the screen. That's the server I have to go to now. That's my bank server. But the moment I will look into this address, I need to send a HTTP GET request to get a web page from the first page from my bank web server. But again, in the background, my client will generate a ARP request for this IP address, and it knows that this ARP does not sit locally on my machine. So what will he do? He will ask the router MAC address, which is already there in my machine, to forward this packet towards the router now. So this time I will just use the router's MAC address by doing a local ARP query and finally move the packet from my machine towards the router. Router, which is also called as a next hop. But to do this, because my HTTP GET request has a destination IP address as 111.10.202.15, therefore it will ask for a MAC address of a router, because my machine will know that this cannot find out a MAC address, because that particular bank server is not sitting directly on layer 2/layer 3 switch. So what will happen now? The router will start moving this packet of HTTP GET request towards the bank, which we will now assume that yes, it will automatically reach there, because we know that internet will take care of. So this completes my web request. Without your knowledge, imagine if you're doing this 100 times to go to any website. Please understand whatever we have discussed in the last 2 slides. If I'm sitting in my office, which has all similar infrastructure like a layer 2/layer 3 switch, a router, and then a modem, and then it goes to the internet. Imagine all this is what is happening with every new request that I generate for a bank or a mail or whatever. But yes, if I am in my broadband connecting directly a Wi-Fi router in my infrastructure, maybe 1 or 2 steps will happen less. But behind the scene, the browser and my machine is doing all this. Let's go to now a third example, where now we are wanting to access the mail from client B. Now the client B wants to go this time to a mail server. By now, imagine this client B has also done some web in the past, and it already knows that I don't need to do a ARP resolution to discover my DNS server. I already know that my DNS server has to be reached by a router only. So that's the only difference you will see, that it will pick up from a ARP table cache on the client B itself. So as and when I keep on learning the MAC addresses where I have to push the packet to as a machine, I keep on adding my own machine's ARP table, which is called as a dynamic ARP table. And with every power off cycle on my machine, my ARP table gets wiped out. So if I've just powered recycle my client B, you will see that yes, the whatever way the example 2 was, this entire example repeats itself the same way. But if my machine B has been switched on since morning, by now it has already understood that the DNS server will only be reached by the MAC address of the router, not by its own MAC address, because DNS server is not directly sitting on my local layer 2/layer 3 switch. So the example 3 and example 2 are not different. These are just doing the same thing, except for making you understand that yes, there is something called as a local ARP table on each client machine which gets built. So this is just a repeat of what you have seen, that okay, client B will now start sending a mail. Now this time it will do a mail resolution from that same DNS server. So it will come to know that okay, mail server is having this particular IP address, and it will start moving the packet towards the mail server. But then it will, after ARP discovery, it will come to know that yeah, this is not sitting on the local machine, so he has to go towards the router alone again. And router's MAC address he already have in his table, so he will send the mail packet. So the mail packet will start from 192.168.10.76 machine. This mail packet has a destination as 97.53.157.209. But we all know that the packet cannot move until unless it has a MAC address on this wire. So what will it do? It will, he knows that 97.53.157.209 MAC address is not known to me. So it will start querying for the MAC address for the next hop, and that is router, who is going to take machine B out of this network towards the internet. And then obviously once I know my destination MAC address is the router, the switch knows that the port number 12, which is physically connecting this client B, will need to be moved for the packet to the port number 1/1, which is my router port. Now let's look at the example number 4. This is little different than example 2 and 3 and the one which we did. But it is important to look at this example as well. But before I do for this example, is there any question? Next 1 minute if anybody has a question. Okay, thank you very much. I believe everything is so far going okay. One more thing I would like to check. Is the voice and the clarity okay? Any
It's
one
good,
of you
sir.
can? Yeah, okay, thank you.
It's loud and clear, sir.
Yes, sir, it's okay.
Yeah, thank you very much. Yeah, so now let's understand the example number 4. In the example number 4, the business need or the business use case is that there is a surveillance camera 192.168.10.107. This surveillance camera is connected on port number 1/17 on this switch. And this surveillance camera is doing a real-time recording. And all this real-time recording has to be dumped or continuously stored on a storage system, because this device does not have enough capacity to locally store the content. So it needs a continuous session to be storing it on a storage server. Now, storage server is in a different building. And it is in a different building, but physically connected to my own, within my campus itself. So this is taking me a storage server directly connected on physical port number 1/24. So now just go back to that table which I've shown you somewhere in the middle when I was saying look at the last entry. This is 192.168.11.19. Now this machine is a big storage closet in my office, kept somewhere but on a different IP schema. When I say different IP schema means it is not having my first 3 octets common with my own client based LAN. So if you see 192.168, the third octet is 10 for my client A, B, printer, camera. But for the storage server, in the third octet space, I have 11, which means it is beyond my local network. It is beyond my local segment. And how will it discover this? By the subnet mask, which we are not discussing in this chapter today. But with that, all machines which are on 192.168.10 network, they know that 192.168.11 is not my local network. So my local ARP will not work, which means I will not be able to get to know the MAC address of 192.168.11.19 by doing a local ARP resolution. It will not work. So what I need to route. I need to switch using layer 3 functionality, because I know that if I don't know the MAC address of my end device, how will I work? It will not happen that way. So therefore, now let's start seeing at the traffic flow what will happen. When the camera is triggered for a continuous storage, for a real-time surveillance, as we have already discussed the business use case. The camera IP address is 192.168.10.107, and it starts the packet for storage server with the 192.168.11.19. In the third step, the camera will realize that no, the storage server is not on my local machine, local segment, sorry. So if it's not on my local network segment, hence the local ARP will not fetch me the MAC address of the destination machine. So what should I do? So it will request for a layer 3 functionality. And for that, the layer 2 switch will convert itself or enhance its capability to a layer 3 capability, because it's a layer 3 switch in real. It will say my friend, don't worry, camera. I will give you a direct access, because my switch table, which also has a MAC address of this guy, I will use a layer 3 routing function for you. Don't worry, because the guy is directly sitting on me. That's how you don't see the need of 192.168.10.1 router, because I don't need to go to the internet. I am within my own campus. So this time, instead of giving back or getting a router LAN IP address to move my traffic towards the internet, I will let my layer 3 switch help me forwarding the packet, because it knows that the MAC address of the storage machine is locally there on my MAC table, but with a different IP segmentation. So a layer 3 functionality and a layer 2 functionality works together on this switch. That's why you will see I have shown this as a layer 2/3 switch. But when you look into the books, you will not see it as 2/3. Also, I'm not trying to tell you that either it will work as layer 2 or it will work as layer 3. But this is just like 2 plus 3. Both functionality the same machine will do, and my packets will work. I will now go back to this table which we have built in the beginning, so that we all know, yes, what we are talking. Look at this. This is a beautiful layer 3 table, because it knows what should I do. And with the current generation of layer 3 switches, this functionality is embedded into a single switch table. Now, to come back to this particular example, what is the basic difference between a layer 3 switch and this router which I am seeing in the bottom? Fundamentally, they are doing layer 3 job, I have understood. Fundamentally, they will help me if I don't have a local MAC address. Fundamentally, they will connect me either by their own MAC address if a traffic has to go to internet, or they will help me short circuiting the MAC table by helping me that the traffic will move from port number 17 to port number 24 directly in this last example, because at the end of the day, the switch will have a common table. He is aware about that MAC address. But what is the basic difference then? The only basic difference which can be realized in this particular looking at the diagram is one, that the layer 3 switch does all the functionality through something which is called as a application specific integrated circuit, ASIC. So its forwarding speed is amazing. On the contrary, the router is a software routine function, and that software routine function is not executed as an assembly language code in a processor or any peripheral. It is a software program, and we all know that a software program is much slower than the ASIC based program, because that's purpose built for the functionality is embedded on the hardware itself, chip itself. So this is the one very important difference. Now, looking at this kind of a scenario, if you look, when I am moving a surveillance camera traffic, I need my use case to continuously throw the traffic at a very high speed and in a very big bulky packets. Therefore, I need a layer 3 switch capability there. However, when I'm going to an internet bank or my mail server on the internet or my DNS server hosted on the internet, I don't need that kind of big packets to move, or I don't need at least that kind of a speed to move, because the internet itself is aware that the entire traffic flows sequentially or serially. Hence, the software programming on the router is good enough for me to get my purpose solved. And in the beginning itself, I have told you fundamentally from a layer 3 routing / forwarding packet functionality, they both are doing the same job. Another important thing on the router slash switch, which I would like you to, if you have to write down, please write down. On the switch, you have seen this slide. I will show you backwards. Sorry. That generally the downstream is 1/10 giga Ethernet. However, the upstream is again 10/40/100 gig. So these are the very limited options for the upstream which are available. But when I come to a physical router, this router, it allows me to connect with the very, very diverse world. The diverse world, which would be a modem on the other side, which you are seeing it here. And there are plenty of options which exist here. However, on a layer 3 switch, we do not offer all these functionalities. We only use Ethernet standards, the gigabit Ethernet standards, to physically connect. So standards is a word which is used for layer 1, which means how a physical electrical / mechanical connectivity will happen. On a layer 3 switch, you will see typically a fiber optic cable or a copper cable with a RJ45 jack. That's a mechanical connectivity. And then electrically, this is, or optically, it is supported with very limited options. Gigabit Ethernet is a electrical / mechanical standard, or gigabit Ethernet on a fiber. It's an optical standard. And in the optics, you will see either a short range or a long range fiber with a multi-mode or a single mode. So those are the very few limited options. But when we are connecting towards the internet, there is a huge diversity which will require different types of electrical and mechanical interfaces physically to be connected. And whenever we are going towards the internet, we always know that the traffic will always move serially. So I don't have to have a very high express forwarding kind of features on this. So this distinguishes the router. So now let's go to the next slide to further delve into all this. Okay. Whatever I have told you, I am going to now specifically fix myself to this router, which you are seeing in this slide in the extreme right, left, looking at the screen, extreme left bottom, 192.168.10.1. Why it is so beautiful? Why it is so capable to take and still exist in the networks? This particular picture is from cisco.com. So I attribute these two pictures to them. Then moving on to the routers, you will look into the functionality. We all understood that they are going to forward the packets serially, I've already told you, and using the software routines, but not the ASIC functions. Then connectivity. Downstream is, which means if you look at this diagram, in the downstream is that yellow color cable, which is taking it towards the layer 2, layer 3 switch. Upstream is that cable which is taking towards the modem. Okay. So the upstream possibility, now let's look at this. All of you can write down these terms and do your individual research if you are interested in, and if you have not heard about them earlier. MPLS, multi-protocol label switching. Amazing way. Very prevalent way to connect the networks across the globe, within the country, within the city. Very powerful technology. Almost been into existence since last 18 years. SDH stands for synchronous digital hierarchy. Very powerful, into existence for last 30 years. And SDH, we all have been hearing, if we are electronic students or who already have a data center experience, they must have been hearing what is an even link. Even link is 2 Mbps. Then T1 link. T1 link is 1.44 Mbps. Then multiple even links combined together to make a E2 link. multiple E2 links combined together to make a E3 link. So there is a hierarchy, E1, E2, E3, and then it starts becoming OC, OC1, OC2, and then it becomes STM1, multiple OCs, 12 OCs combined together. So this is how, this is very, very powerful time division multiplexing based model, where the packet is multiplexed on the single physical wire, and you are able to host multiple channels on the single wire when it moves on the external internet towards internet side. So how many of you have internet which is beyond 2 Mbps? All of us will laugh, correct? But when I started my career, getting a 2 Mbps internet was like a affair of nothing less than 25 lakh rupees for a company. And when we used to have that, those service providers, they used to take one E2 stream and were segregating that into multiple 2 Mbps pipes. Forget about that. People were getting even 64 kbps internet lease lines by paying almost as good as 7 to 10 lakh rupees way back in 2001-2. So how from a 2 Mbps we were able to bring it down to 64 kb again was a time division multiplexing. Okay, so that was a technology. Then we had another technology which is not very much in existence, but in the legacy networks you will come to know still exists, is the ISDN. This is also one of the digital networks, started in year 2000, 1999 to 2000, so almost 2 decades old. Then asynchronous transfer mode, very, very powerful WAN infrastructure network. Frame relay, almost obsolete, but used in some of the, again, legacy networks. Point-to-point protocol, PPP. RF link, which is a radio frequency. And in the current times, most of the large-scale banks, large-scale companies, they are not taking internet in their buildings on time division multiplex networks. They are taking in something called as a wavelength division multiplex, WDM, very, very powerful. So MPLS, WDM, all these, they have to coexist these days on these routers. On the type level, so a router will never do a job of a layer 2 function. And we should never ask him to do that, because it will become very, 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 it will become a erratic device if you put it to do a job of layer 2. So it is a layer 3 function. Now comes the very interesting thing, which you have to, again, I solicit you guys to write down if you have to, or if you were aware, it's a great thing. And also I request, if somebody is not muted, please mute yourself. Yeah, thank you. Functionality wise, a router will do two things. Routing. In a technical terms, routing means finding the path. Finding the path means, how will I go from Delhi to Bangalore? Or how will I go from Delhi to New York? Or how will I go from within Delhi from Nehru Place to Vasant Vihar? All this is what is required to be understood. And that finding of the path, and not just finding the path, but finding the best path, is called as a routing function. And once the path is identified, start moving the packet. So there is a chain of routers which connect together. And the only job a router does is move the packet to the next, and doesn't care where is it going subsequent. Whether the application will meet another application or not, that's not what is the problem of a router statement. It never solves that problem. It only says, I will only take you to the next hop, period. Now your next hop has to decide whether whom to take to the next hop, and so on and so forth. So this way, the routing systems keep on building and talking to each other as the routers. Now, when we are building these infrastructures, let me come back to this slide subsequently. So this is the last slide, but I will come back to the prior slide. We are almost at the closure. One has to understand that these routers of the current times, in the last few years, have been evolving themselves to something called as the software-defined networks. You guys need to know, even if you are a consultant or you are a researcher in QoS/Purple Synapse, or you are going to be a sales guy, because your customers are going to use these words or already using these words for almost few years now. So a software-defined network. Firstly, let's understand, we all have been so far talking about the layer 3 switches and routers. Both these devices have two roles. Just now I have spoken. Routing, that is a decision to find and fix the path for routing/switching the packet. And the second role they do is forwarding, which is actually moving the packet to the absolute next hop or the end device, if it's a leaf object. But then, why are people talking about SDNs, or what is there inside the SDNs? Let's understand. Hence, let's start looking at what we are building with these routers and switches so far in many years, in last 2.5 decades. What we have built with routers and switches, let's understand. Hence, we build the hierarchical mesh to create internetworks, where every hop does these two functions. Now, when the network has become so big, it has trillions and billions of devices, and trillions of IoT devices are expected to join this particular internetwork. This has already become very highly taxing for two reasons. One, complex routing decisions have to be taken by each of those devices, correct? Each one of them is expected to maintain a layer 3, layer 2 switching table, correct? Or a decision tree where they can move the packet to the next hop or to the right hop. Besides doing the routing and switching, which means actually physically they have to move the packet from one physical port to another physical port. Apart from that, they have to maintain that routing intelligence decision onto their device. This has resulted into two problems. One, the delays, growing delays because of this growing complexity, and growing difficulty in troubleshooting the issues whenever an issue happens. Consequently, the networking equipment giants have come up with a solution to separate the switching function from the routing function. Let's separate these two things, because the router/layer 3 switch was doing these two things. And when we are segregating these two functions, we will let the physical device, which need to connect to physical ports by machines or by next hop devices, that hardware device will only do a packet forwarding/packet moving function. However, the decision to maintain routing trees, complex routing trees, that will be defined by a software which will be taken out of these devices into a manager or a master called as a policy manager or a master. This new way of working for the routing and layer 3 switching devices is nothing but software defined network. Examples: Cisco ACI, OpenFlow. So you guys are okay to now look into these. So I can do it at my layer 3 switch or at my router. The broader term is software defined network. But when I'm only doing at my WAN facing routers, the router that was 192.168.10.1 in our diagram so far discussed, the device which is taking my packets toward internet, towards my external networks, that device, since it's a part of a wider area network, the network which is connecting it to a wider areas of network, therefore the same SDN, when only deployed in the wider area network of my organization, it has a different abstraction called as SD-WAN. So SD-WAN is nothing but a SDN of the WAN. Here we have some companies like Velo, and in India particularly there is an India origin company based out of Bangalore which is becoming very, very big now, is called level networks. So these guys are bringing the WAN, which is currently very, very popularly deployed with the very, very deeply deployed network called MPLS across the globe, within the country, within the city, within the continents, within the globe. They are trying to substitute it completely or coexist with that. So they are moving block by block, the entire WAN, slowly and gradually, from a typical MPLS to SD-WAN. This is what is happening around us in the networks. Apart from that, we have to understand that Wi-Fi is also very popular and a very important technology. There are two types of Wi-Fi which are coming up or already there in the existence. One is the enterprise level Wi-Fi, which we always see deployed for us in our offices, in the cafes, in the hotels, in the room of hotel where we are staying, or in the conferences somebody gives us. And then there is also industrial grade Wi-Fi. So for example, we are going to work for a petroleum refinery company, and therein we will see that all those drones which are doing surveillance, because there is no physical camera, there is a drone. You know, unlike the diagram where we have seen that a physical wire was coming from a camera getting into a network, or we have seen in the first diagram which was there where Wi-Fi devices, Wi-Fi printer were connected to access point. Yes, the same will happen. But we all know that the access points which we deploy in our offices, in the hotels, they have very limited range and they cannot handle much of the terrain. But in the refinery, which is spanning across square kilometers, it is not so easy to deploy a enterprise grade WAN or Wi-Fi. So what we need are industrial grade Wi-Fi. So these are the two different Wi-Fi abstractions which are existing. Also, we have to understand that this is the kind of network racks or the data centers which are having. When the people work in these data centers, they don't see monitors, you know, what we see for every device, the monitor is connected. They will remotely connect through their laptops. So remote administration is also coming up to manage these data centers, which we are going to discuss in the second section of our presentation. Lastly, but not the least, all these data centers have to be protected against the fire and other heating problems. So they are having all the designs and the planning done in such a way that it gives a great amount of cooling. Fans are taking care of the heat which is building around in these. Plus, they have the fire protections that are waterless, not the water oriented, not the liquid oriented uh, fire extinguishers. So this all is happening around us. This slide I've already explained. Now, what are the goals for us when we are looking from a cyber security perspective towards the networks? The goals for us are, first of all, we need to protect the network devices from getting compromised. You know, the routers, the switches themselves should not get compromised. So what we have to do for this reasoning is, we have to achieve this by keeping track of the system logs. So that's one opportunity. As a security consultant, we have to look, whenever we are looking as a security consultant, we need to see whether can we pick up the logs from our routers through a functionality called syslog. So you guys can write down this to read more about syslog. The second objective which we have to address to get the protection for the network devices itself is, we have to strengthen their administrators' authentication and authorization levels. Authentication means the one itself is allowed to access the device or not as an administrator. Second, the administration may have multiple levels of roles. You know, somebody who is allowed to only read the configuration, somebody who is allowed to only play with the downstream configuration, which means he is allowed to add the machines only in the downstream, but he cannot do anything on the upstream infrastructure because upstream will impact more people. And somebody who is a root level or a global administrator for entire functionality. So all these are authorization levels. So we need to strengthen the security for administrators who have a privilege-based access for their both authentication as well as authorizations, and substantiate it further by recording or auditing their tasks, what they're doing when they are in a privilege mode of access to these devices. All this is achieved by an industry functionality today called as PIM and PAM, Privilege Identity Manager, Privilege Access Management. So these are the tools which are beyond the scope of this discussion, but you can understand these ones we will talk about in the security in the subsequent sections of this presentation theme. Then we have to do the configuration assessment, that is, do a security audit to discover and remediate the configuration faults that might exist on the routing/switching devices. So that's a third avenue from security consulting point of view, or when you go as a consultant or a solution designer, that where the problem can exist. Okay. Then comes the fourth, do a vulnerability assessment, which means if this router comes from vendor X, is there a possibility that this vendor has just published a vulnerability, or has the world discovered some exploit that can exploit this vulnerability? So one has to do that exercise to find out if there is any possibility to hijack, compromise, or take over this networking device as a hacker. So that activity or access role as consultants, as QoS, what one can do is doing a vulnerability assessment and penetration testing. So these are the four basic scope areas when we have to see the goals of cybersecurity from networking point of view as a consultant. Now we have taken care of device security, imagine, by doing these services or these work functions. There is another problem which these devices foresee or record or understand, and that is that these devices participate in processing the unsolicited traffic. These devices are very, very sophisticated, nicely, these are nice components on the in the network. They are told to forward the packet. They are told to keep on growing their decision trees for routing whenever they learn a new path which exists, or whenever a existing path flaps because the network cable goes bad, or the network link goes bad on one of the existing paths. So these guys are doing beautiful job, but somebody who has the understanding of this infrastructure actually use this function to abuse this capability. And if somebody is abusing this capability, then these poor devices are actually participating in helping amplifying the attack, or helping somebody to use them to be throwing that unsolicited traffic on the machines. If we as the security consultants have to identify what is the opportunity or a scope that exists for us, is we have to real-time monitor these system logs. Already what we have told you in the first step, syslog. So syslog is a very powerful, it not only gives the system information, it also gives the information about the other attributes, like how much is my memory utilization. So if my memory utilization was just 50% in a normal operation, and now my syslog starts seeing and honking that, oh, it is now going up to 80%, 90%, and that's an abnormal behavior, one has to look into this, and that will only happen once we are doing a real-time monitoring of these syslog functions. Second, all these current generation routing/switching devices, they maintain flows. The flows is a full packet understanding. Packet means the network layer packet, which has also the understanding on an application step. So let's say it's not just the networking information, but whether it was a HTTP packet or a SMTP or a FTP or a other application traffic packet. So they understand that type of application packet information is there, which is the client that was accessing, with what is the destination IP address or a destination MAC address. So all those informations are stored. Now, for example, some vendors like Cisco, they store that information in something called as a NetFlow. Juniper does in the JFlow, and so on and so forth. So these are flows. These heavy flows carries lot of information what is happening in the network plane. And the security opportunity that exists is if you start doing a real-time monitoring of these flows. You can write down one more term. The real-time monitoring of these flows is at times also called as NBAR, Network Based Application Recognition, NBAR. Okay. So when you are doing a real-time monitoring of a syslog, or you are doing a real-time monitoring of the flows by virtue of NBAR, or you are doing both, whatever, these are the opportunities that will help building the security posture or enhancing the security capability to detect these attacks or issues. Also, we have an opportunity to build the anti-DDoS capability. So whenever these devices start seeing something abnormal, they can trigger these anti-DDoS functions. So that anti-DDoS functionality, DDoS stands for a distributed denial of service attack. This functionality is also a scope which comes under the cybersecurity team.